In this video, we are going to discuss about discrete time signals and classification of discrete time signals. We know that signals is a physical quantity that varies with time, space, or any other independent variable. Some examples of discrete time signals are speech signal and ECG signal. Discrete time signals are defined at discrete instance of time. We consider measurement of a person's body temperature per hour as a discrete time signal. Every continuous time signal can be modeled as a discrete time signal if it is recorded at discrete instance of time. Discrete time signals are continuous in amplitude and discrete in time. That is, the amplitude is varying as to 1.7, 1.7, 1.2 like that. But we are measuring the amplitude only at the time periods 0, 1, 2, 3, 4, etc. Discrete time signals are represented by x of n. Continuous time signals are represented by x of t. We studied about elementary discrete time signals already. They are unit sample sequence or unit impulse sequence. That is, del of n is equal to 1 if n is equal to 0. That is equal to 0 when n is not equal to 0. Next is unit step sequence, where u of n is equal to 1 if n is greater than or equal to 0. It is equal to 0 if n is less than 0. Next is the unit ramp sequence, where u r of n, which is equal to n for n greater than or equal to 0. Meaning is, when n increases, ur of n also increases. When n is less than 0, it is equal to 0. Next is the exponential sequence, where x of n is equal to a power n for all values of n. The signal increases exponentially or decreases with respect to the value of a. Now we are going to see the classification of discrete time signals. They are energy and power signals, periodic and aperiodic signals, symmetric and antisymmetric signals, or even and odd signals. First category we are going to see is energy signals and power signals. Energy of a discrete time signal x of n is given by E, which is equal to sum of n is equal to minus infinity to infinity modulus of x of n the whole square. If this energy calculated is finite, then we can call the signal x of n as a energy signal. The average power of the discrete time signal x of n is given by P, that can be calculated by limit n tends to infinity 1 by 2n plus 1 summation n equal to minus n to n modulus of x of n the whole square. Suppose if we consider this term is equal to the energy of the signal. Actually, energy is varying from minus infinity to infinity. If we are considering this as a finite energy as En, then the power of the signal we can write as limit n tends to infinity 1 to 2n plus 1. The remaining terms we are represent as En. If the calculated power is finite, then the signal is called power signal. If energy is finite, power is equal to 0. If energy is infinite, power can be finite or infinite. If energy is finite, we can call it as energy signal. If power is finite, we can call it as power signal. Second classification of discrete time signals are periodic signals and aperiodic signals. A discrete time signal x of n is periodic with the period n if and only if x of n plus the period n is equal to the original signal x of n. This is an example for periodic signal. Here the signal is repeated after a particular time period. The smallest value of n for which the periodic condition is true, we are calling it as fundamental period. If there is no value of n that satisfies the periodic condition, is called non-periodic or aperiodic signals. The property of discrete time signal states that discrete time sinusoids whose frequencies are separated by an integer multiple of 2 pi are identical. Consider this discrete time signal x of n is equal to a sin omega naught n plus theta. If the signal is periodic, x of n plus capital N is equal to x of n. So for this signal, if it is periodic, x of n plus capital N is equal to a sin omega naught n plus theta. So which is equal to a sin omega naught n plus omega naught n plus theta. If it is periodic, this signal is equal to a sin omega naught n plus theta, that is equal to the original signal. This will happen when this term omega naught n is an integer multiple of 2 pi. That is, this omega naught n must be equal to 2 pi into an integer. In that case, this term is changed to a sin omega naught n plus theta, which is actually equal to the original signal. Then omega naught is equal to 2 pi m divided by n. Therefore, for the discrete time signal to be periodic, the fundamental frequency must be a rational multiple of 2 pi. Now, the fundamental period n is equal to 2 pi m by omega naught. That is only represented here. Third classification of discrete time signals are symmetric and anti-symmetric signals or even and odd signals. A real valued signal x of n is symmetric or even if x of minus n is equal to x of n. X of minus n corresponds to negative values of n, x of n corresponds to positive values of n. A signal x of n is called antisymmetric or odd if x of minus n will be the negative of x of n. If x of n is odd, then this x of 0 will be equal to 0. A signal x of n can be represented as a sum of even and odd components. That is, x of n is equal to even component of x of n plus odd component of x of n. E corresponds to even component, O corresponds to odd component. If you are replacing n by minus n in this equation 1, x of minus n is equal to xe of minus n plus xo of minus n. Here x of minus n is equal to, this is an even part, so x of minus n is equal to x of n. This is an odd part, so x of minus n is equal to minus of x of n. So when you are adding these two equations, x of n plus x of minus n, these two terms are getting added, so it is equal to 2 into xe of n. These two terms are subtracted, so it is equal to 0. Therefore, xe of n, even component of n, is equal to 1 by 2 into x of n plus x of minus n. Subtracting equation 1 and 2, x of n minus x of minus n, which is equal to xe of n minus xe of n, which will be equal to 0. X naught of n minus of minus x naught of n, so which is equal to 2 into x naught of n. Therefore, x naught of n is equal to 1 by 2 into x of n minus x of minus n. From this 2, we can obtain even component of x of n and odd component of x of n. So in this video, we have discussed about discrete time signals and its classification, such as energy signals and power signals, periodic and aperiodic signals, symmetric and antisymmetric signals. Thank you for watching this video.